Somewhere beneath one of the most photographed mountains in the country, something has been moving that most people will never notice in their day-to-day lives. In the summer of 2025, the ground underneath this mountain rattled with more earthquakes than it had ever produced in the entire history of modern monitoring. Over 1,300 separate tremors in about 7 weeks, the biggest swarm ever recorded there. More than 100,000 people live in towns that sit directly on top of mud and rock left behind by this same volcano's past outbursts, and most of them drive past that danger every day without a second thought. This isn't the kind of volcano story built around fire and lava bursting into the sky. This is a story about ice, about water, about solid stone, slowly turning into soft, crumbling clay deep inside a mountain, with almost nobody paying attention until the ground itself began shaking in a way scientists had never witnessed before. Is this volcano getting ready to erupt? Why did it shake so violently in 2025? And why do the scientists who study it lose more sleep over ice and mud than they do over lava? Let's get into it. To understand why this particular mountain unsettles scientists more than almost any other volcano in the country, you first have to understand how danger gets ranked in the first place. The United States Geological Survey keeps something called the National Volcanic Threat Assessment, ranking every active volcano in the country by risk. The twist is that this ranking has almost nothing to do with how often a volcano erupts. It's about how much damage an eruption, or even just volcanic activity short of an eruption, could cause, and how many people live close enough to be hurt by it. A volcano sitting in an empty stretch of wilderness could erupt constantly and still rank low, simply because nobody lives near it, while a volcano that barely erupts at all but sits right next to millions of people can rank near the very top. That single distinction changes the whole way you have to think about which mountain actually deserves to be called dangerous. Most people assume the most dangerous volcano in America has to be the one erupting. Most often, and by that logic, Hawaii's Kamalauea wins easily. It's been erupting almost continuously since December 2024, cycling through burst after burst of activity, some of it sending lava more than 1,000 feet into the air. But erupting frequently isn't the same as being the most dangerous. Kilauea sits in a place where lava flows can usually be tracked and watched as they creep across the landscape, giving people time to get out of the way. So even with all that constant activity, it doesn't carry the same kind of sudden, hidden danger that tops the USGS list. The volcano that actually sits at the very top of that list looks nothing like a fiery, constantly erupting mountain. It sits quietly in western Washington state, and on a clear day, you can see its icy summit from downtown Seattle. That mountain is Mount Rainier. For years, it has held the title of the most dangerous volcano in the United States. And here's the strange part. It's not because scientists think it's about to explode violently or erupt often. It's because of one specific feature that almost no other volcano its size in the country carries in the same combination. To understand that feature, you first need to understand what Rainier actually is. It stands just over 14,000 feet tall, the tallest volcanic peak in the lower 48 states. But height alone isn't what makes it dangerous. What makes it dangerous is what's sitting on top of it. Rainier carries the largest glacier system found on any single mountain in the lower 48, somewhere between 26 and 28 named glaciers, wrapping its slopes like frozen blankets, together covering more than 35 square miles of permanent snow and ice, roughly the equivalent of covering 17,000 football fields with frozen water thick enough to bury a house. Now picture all of that sitting on top of a mountain quietly cooking itself from the inside, slowly turning solid rock into something closer to wet clay. It's a bit like building an enormous snow fort on top of a sandcastle that's being soaked very slowly by a hose you can't see. From the outside, the fort looks solid. Underneath, the sand holding it up loses a little strength every year. Here's a comparison that makes that feel real. Scientists estimate Rainier holds roughly 8 times as much glacier ice as Nevado del Ruiz, a volcano in Colombia, once held. Back in 1985, Nevado del Ruiz erupted and melted the ice on its summit, and that meltwater mixed with rock and ash into a wall of mud that buried the town of Armero, killing more than 23,000 people in minutes. Rainier sits on roughly 8 times more ice than that mountain ever carried. That comparison is a large part of why volcano scientists don't rest easy about this particular peak. Here's what makes Rainier different from almost every other volcano along the Ring of Fire, the chain of active volcanoes circling the Pacific. Its biggest threat isn't lava, and it isn't even falling ash, even though ash can cause real headaches for aircraft and farmland nearby. The biggest threat, the one with emergency planners running drills year after year, is something called a lahar. Understanding what that is and how one forms is the key to this entire story. A lahar is a fast-moving river made of mud, water, rock, ash, shattered trees, and boulders, all rushing downhill together, something people who have witnessed one compare to wet concrete moving at highway speeds. The word itself comes from Indonesia, a country that has suffered some of the deadliest mudflow disasters on record. And here's the single most important fact in this whole story, the one detail most people get wrong. A lahar doesn't need an eruption to happen. It doesn't need lava or an explosion. All it needs is heat, water, and rock that has been weakened over time, and unfortunately for the communities near Rainier, the mountain has plenty of all three, stacked directly on top of each other, whether or not it ever produces another drop of lava again. So how does this actually happen? Deep beneath Rainier's icy summit, molten rock has been slowly heating underground water for thousands of years. That superheated water and steam doesn't just sit still, it pushes upward through cracks and tiny openings in the volcanic rock, and as it travels, it changes the minerals in the stone around it. Strong, solid volcanic rock slowly turns into something closer to soft, crumbling clay. Scientists call this hydrothermal alteration, and it has been happening inside Rainier for an extremely long time, almost like a slow leak nobody can see from the outside. Think about leaving a metal spoon in a hot cup of tea for a very long time. The heat and liquid slowly change the surface of that spoon, even though nothing seems to happen in the first few minutes. Now stretch that idea across thousands of years, deep inside a mountain, with scalding water and steam constantly moving through cracks instead of a spoon in a teacup. Over time, the rock doesn't just warm up a little, it changes what it's made of, turning from something hard and strong into something soft enough to dig out with your bare hands. That process is quietly working away beneath Rainier's summit right now, while hikers take photos on the trails above it. Because of it, large parts of the upper mountain are no longer solid rock. They've become weak, waterlogged material sitting on a steep incline, held in place mostly by its own frozen weight and by plain old friction-fighting gravity. Now picture stacking 35 square miles of a heavy glacier ice directly on top of that weakened rock. What you get is close to a natural time bomb, except this bomb doesn't need a volcanic eruption to go off. A strong earthquake could trigger it. A sudden heavy rainstorm on already soaked ground could trigger it. A fast burst of glacier melt during an unusually hot summer could trigger it. Even a landslide with nothing to do with an eruption at all could shake loose enough weakened rock to send a wall of mud and debris crashing into the valleys below. This isn't just a theory. It happened roughly 500 years ago in an event geologists now call the electron mudflow. There was no eruption that day, no lava, no explosion, just a section of weakened rock on the mountainside that finally gave way, mixing with melting snow and glacier water as it roared downhill toward what is now the Puget Sound area, burying the land beneath a thick layer of mud and rock. That single event is some of the clearest proof scientists have that Rainier doesn't need to erupt to become one of the deadliest natural hazards in North America. Which brings us to why the summer of 2025 matters so much to this story. Early on July 8th, instruments buried around the volcano began picking up earthquake after earthquake in a tight cluster scientists call a swarm. Under ordinary conditions, Rainier produces around 9 or 10 small earthquakes a month, the mountain's quiet background heartbeat. Every so often, it experiences a short burst of extra shaking once or twice a year, considered completely unremarkable. What started on July 8th, 2025 was nothing like that. In the first 12 hours alone, researchers recorded more than 40 earthquakes an hour at the busiest point. By the end of the first week, over 1,000 quakes had already been located, and by the time the swarm slowed in late August, the total had climbed past 1,300 events, with some experts believing the true number was even higher once you factor in the smaller quakes too faint to detect. To put that in perspective, the previous record happened back in 2009, around 1,000 small earthquakes over just 3 days, the strongest only a magnitude 2, 5. The 2025 swarm didn't just match that record, it blew past it, both in sheer numbers and in how long it lasted, stretching nearly 7 full weeks instead of 3 days. While all of this happened underground, life above ground looked completely normal. Hikers kept climbing toward the summit. Families kept driving through nearby towns with no idea that instruments buried in the earth were quietly recording thousands of tiny tremors beneath their feet. Word spread slowly at first, mostly among scientists watching their monitoring screens, before it reached local news and worried residents who all wanted an answer to the same question. Was the mountain about to blow? That question pushed the United States Geological Survey to move quickly through every check available. Rainier has been watched closely for decades, with an original small seismometer network growing into dozens of sensors spread across the slopes and valleys, feeding data back every second of every day. That long history of quiet, uneventful monitoring is exactly what allowed scientists to recognize, with real confidence, that the summer of 2025 was something genuinely unusual. First, they checked ground deformation using GPS stations to see whether the mountain was physically swelling or bulging outward, the kind of change you'd expect if magma were pushing toward the surface. They found nothing. No swelling, no sinking. Next, they checked infrasound sensors, instruments that pick up extremely low sounds too faint for human ears, the kind that can come from rock falls or small surface explosions. Again, nothing unusual. Then they reviewed webcam footage of the summit and upper slopes, watching closely for any change in the fumaroles, the steam vents where the mountain's hot water system reaches the surface. Nothing out of the ordinary there either. Then came the boldest step. On August 4th, the USGS teamed up with the National Park Service to fly a helicopter directly over Rainier's summit craters, sampling the gases escaping from the fumaroles in the east and west crater. If magma were really rising toward the surface, scientists would expect a clear shift in the chemistry of those gases, usually a jump in sulfur dioxide relative to the others present. The results came back almost identical to earlier measurements. No meaningful shift in composition or output. No single warning sign at a volcano tells the whole story on its own, which is why scientists layer so many tools together instead of relying on just one. An earthquake swarm alone doesn't tell the whole story, nor do gas readings or ground swelling by themselves. Only when all of these signals are stacked together, like puzzle pieces fitting into place, does a clear picture form. And in the case of the 2025 swarm, every piece pointed toward the same calm conclusion, even though the sheer number of earthquakes made it look alarming at first glance. So, if it wasn't magma, what caused more than 1,300 earthquakes to shake one of the most closely watched volcanoes on the planet? The leading explanation is hydrothermal fluid movement, the same hot water and steam system that has been turning strong rock into weak clay for thousands of years. Scientists believe pulses of that hot fluid move through existing cracks and fault lines, acting almost like a lubricant that lets sections of rock slip and slide against each other, releasing bursts of seismic energy. This kind of activity has been documented at Rainier before, just never on this scale or for this long until now. Throughout the summer, USGS scientists were clear and consistent. Despite the enormous number of earthquakes, Rainier stayed at its normal, everyday green alert level the entire time, with no sign the shaking was building toward an eruption. And when they reviewed the full dataset in the weeks that followed, they confirmed the earthquake rate had settled back down to its usual baseline of roughly 10 events a month, the same steady rhythm the mountain has kept for decades. This is exactly the point where it would be easy to swing too far in either direction, and neither extreme is helpful. It would be wrong to walk away thinking Rainier is on the verge of some dramatic movie-style eruption, since the alert level never moved, the gases didn't change, and the ground didn't swell. Every tool scientists used pointed to the same conclusion: a hydrothermal event driven by hot water and steam, not a magmatic event driven by rising molten rock. But it would also be a mistake to treat it as no big deal. Scientists noted the hot water processes behind the swarm might still be happening at levels too small for instruments to detect, meaning smaller bursts of activity could return in the months ahead. And a swarm this large tells scientists something genuinely valuable about how actively fluid and heat are moving through Rainier's underground plumbing right now. Inside a system researchers still don't fully understand even after decades of study. Hydrothermal systems like the one under Rainier can also sometimes produce what's called a phreatic explosion, a sudden small burst of steam and rock caused by trapped hot water flashing into gas, distinct from a full eruption and involving no fresh magma. These can happen with very little warning and have occurred at other volcanoes with similar hydrothermal systems. Scientists keep that possibility in mind, even though nothing in the 2025 data suggested one was building, which is one more reason continuous monitoring matters even during the long, quiet stretches. And this is exactly where the story shifts away from earthquakes and toward the hazard that actually keeps volcano scientists up at night. Rainier's biggest danger was never really about whether molten rock reaches the surface. It's about whether the combination of weakened, hot water damaged rock and 35 square miles of heavy glacier ice above it stays put or finally gives way. And that second half of the equation, the ice, is changing right now for reasons that have nothing to do with earthquakes at all. Glaciers across Rainier have been shrinking for decades as regional temperatures have climbed. But in recent years, that shrinking has sped up sharply, with several named glaciers disappearing entirely, melting, to the point where they no longer qualify as active glaciers under the scientific definition. The same pattern is playing out across the broader Cascade Range and mountain ranges worldwide, from the Alps to the Andes to Kilimanjaro, with some studies suggesting Rainier's rate of ice loss is now several times faster than the historical average. Most shrinking glaciers simply mean less water for rivers or less snow for skiing. At Rainier, shrinking ice does that too, but it also feeds directly into the volcano's biggest hazard, because that meltwater has to go somewhere, and increasingly it rushes down the slopes faster than the old drainage channels were ever built to handle. Every summer now brings surges of extra meltwater far beyond what the mountain's natural drainage was designed for, dragging rock and debris downhill in events park officials call debris flows, smaller cousins of a true lahar. They're not as massive or deadly, but they can still tear apart hiking trails, wash out bridges, and force the park to close areas for safety. Common enough that Mount Rainier National Park now runs regular training for staff and visitors on recognizing one and reaching higher ground quickly. Now, let's talk about who is actually standing in the path of all this. This isn't some abstract danger in an empty wilderness. It's a hazard sitting directly upstream from real towns and real families living ordinary lives, most with almost no visible reminder of what sits above them. Pierce County, Washington, which contains most of the land downstream from Rainier's most dangerous valleys, estimates that roughly 2.5 million people live across the 6 river valleys that could potentially be touched by a lahar in some form. Narrow that to just the high-risk zones, and experts estimate somewhere between 80,000 and 150,000 people live directly on top of old lahar deposits, meaning their towns were literally built on debris left behind by past catastrophic mudflows. The communities most often named in these hazard studies are Orting, Puyallup, Sumner, and Fife, sitting in the Puyallup and Carbon River valleys, the exact same paths historical lahars have followed on their way down from the summit. Orting in particular has become something of a symbol for this risk. A small, growing town built almost entirely inside a mapped lahar hazard zone, where local schools actually run evacuation drills, specifically preparing children for a lahar. Warning going off during class, the same way other kids practice fire drills. These aren't empty danger zones on a map. They're ordinary American towns with grocery stores, little league baseball fields, coffee shops, and neighborhoods full of families. Puyallup is a larger city with busy shopping centers and a well-known county fair every year, and Sumner and Fife sit along major highways that thousands of commuters use daily to reach jobs in Tacoma and Seattle. None of these places feel dangerous when you're standing in them. They feel like home, which is exactly what makes the hazard so easy to forget about day to day, even as schools and emergency officials work to keep the risk from slipping out of mind. To really grasp the scale of what these communities are quietly preparing for, go back roughly 5,600 years to an event geologists call the Osceola Mudflow, the largest lahar to hit Rainier's surroundings in the past 10,000 years. Volcanic activity, or a closely related process, triggered a massive collapse of already weakened rock on the northeast side of the mountain, carving out a crater more than a mile wide as the whole section gave way at once. The landslide transformed into a lahar of almost unbelievable size, picking up so much debris and water that scientists estimate its volume could fill something like 1.5 million Olympic-sized swimming pools. It traveled more than 220 miles from the summit down to the shores of Puget Sound, burying what are now the Duwamish and Kent valleys under a thick layer of volcanic debris. Today, that same ground is covered with homes, farms, businesses, and busy highways, sitting on top of an ancient catastrophe most residents have never heard of. Scientists studying layers of old mud and debris around Rainier have identified at least 11 major lahars that reached the Puget lowlands over the past 6,000 years. That's not a rare, once-in-a-planet's-history anomaly, it's a repeating pattern, and geologically speaking, we're nowhere close to being in the clear. The largest, fastest lahars can race down Rainier's steep upper slopes faster than 100 miles an hour, and even after reaching the flatter lowlands, they can still be moving at 15 to 20 miles an hour. That might sound slow, but this isn't water flowing downhill. It's a churning wall of mud, boulders, and broken tree trunks, heavy enough to flatten buildings, snap bridges, and bury entire neighborhoods in minutes rather than hours. Put those facts side by side, and it's clear why scientists refuse to look away from this mountain even during the quiet years. They point specifically to towns like Orting, Puyallup, and Sumner as places that could see a lahar arrive with almost no warning, especially if the trigger is something sudden like a landslide rather than a slow-building eruption that gives officials days of advance notice. That possibility of almost no warning time is the entire reason this region built one of the most advanced volcano hazard warning systems anywhere in the world, built specifically around this one threat. That system is officially called the Mount Rainier Lahar Detection and Warning System, first set up in 1998 through a partnership between the USGS, Washington State's Emergency Management Division, and Pierce County's Department of Emergency Management. It works through acoustic flow monitors, sensors buried along the mountain's most historically active drainage paths, essentially sensitive microphones tuned to the specific vibration pattern of mud, rock, and water crashing downhill together, distinct enough from a passing truck or ordinary rock slide to avoid false alarms. A real signal streams almost instantly to Washington's State Emergency Operations Center and South Sound 911, both staffed around the clock, ready to confirm the event and trigger the public warning, which connects into the state's emergency alert system along with a network of outdoor sirens placed throughout the most vulnerable valleys. Sensors closest to the mountain pick up a real event first, giving emergency workers a small but precious head start, and every extra second can matter enormously for a family trying to reach higher ground. This warning system hasn't sat still since 1998. Over the past several years, the USGS has run a major project to modernize it, expanding coverage beyond the original Carbon and Puyallup valleys to include the Tahoma Creek and Nisqually River valleys, areas previously left outside the network despite carrying real danger of their own. New stations have gone up around the mountain's east and northeast slopes, above weaker collapse-prone rock along the White River corridor, combining seismometers with infrasound sensors, so responders get multiple independent signals confirming a real event. It's described as the biggest overhaul of Rainier's warning system in its history. And this modernization was already well underway before the 2025 swarm started, which in hindsight looks like remarkably good foresight. There's also something happening in 2026 specifically that deserves attention. Emergency officials in the region have scheduled one of the largest lahar evacuation exercises ever held around Mount Rainier, bringing together schools, hospitals, transportation departments, and everyday residents across the most vulnerable valleys to test not just the technology behind the warning system, but the human side of the response. Picture a school in Ording where an alarm sounds during a normal class period. And instead of a fire drill, students and teachers move toward pre-planned routes to higher ground, while nearby hospital staff practice moving patients who can't walk on their own, and bus drivers, police, and highway workers keep the roads clear rather than clogged with panicked traffic. None of this happens by accident. It takes careful planning and constant communication between dozens of organizations, all built around one goal: getting as many people as possible to safety in the shortest amount of time. These drills matter because, unlike a hurricane where forecasters can give days of advance warning, or even most eruptions, which tend to build gradually over weeks of rising earthquake activity, a lahar triggered by a sudden landslide at Rainier could happen with almost no meaningful lead time. The entire safety margin for tens of thousands of people depends on how quickly a community can go from hearing a siren to reaching higher ground, and that kind of speed is only possible because of drills like the ones planned for this year. So where does that leave things right now, in August 2026, looking at a mountain that just produced the largest earthquake swarm in its recorded history, above communities that have spent the past year watching their warning system go through its biggest upgrade in decades? The honest answer is that Mount Rainier remains at its normal, everyday alert level. There's no sign of magma rising toward the surface, no sign of an eruption on the way, and the extra shaking from last summer has settled back into the mountain's typical background rhythm. But a normal alert level doesn't mean zero risk, and for this volcano, it never has, because the primary danger was never really tied to whether an eruption happens. It's tied to the slow, decades-long weakening of rock beneath the summit, carrying an enormous and increasingly unstable mass of glacier ice on top of it. Scientists describe this not as a question of if a major event eventually happens, but as a question of when, on a timescale that could mean centuries from now, or, in theory, something sooner. What actually changed over the past year isn't the basic danger Rainier poses, which has already been documented and studied for decades. What changed is how loudly the mountain reminded everyone that it's still an active, moving, living system, shifting fluid and heat through its underground plumbing at a scale nobody had witnessed since instruments began watching it directly beneath a glacier system that is, at the very same time, shrinking faster than at almost any point in recorded history. There's a strange contrast at the heart of this whole story. The volcano that draws the most tourists, the one whose snowy silhouette appears on license plates and postcards across an entire state, is also the one carrying the single most dangerous lahar potential in the country. Not because it's the most explosive volcano, but simply because of geography, because of exactly how much ice sits on top of exactly how much weakened rock directly above exactly how many people. Rainier is far from the only place on Earth where millions of people live in the shadow of a dangerous volcano. Naples, Italy, sits at the base of Mount Vesuvius, the volcano that buried Pompeii thousands of years ago, and millions still live around it today. Volcanoes tend to stay quiet for so long that the danger starts to feel like an old story rather than something that could still happen. Scientists who study these mountains know better, which is exactly why places like Pierce County keep investing in warning systems and drills year after year, even during the long stretches when the mountain seems completely calm. Living close to remarkable natural beauty often means living close to remarkable natural risk. And the difference between a close call and a genuine disaster usually comes down to infrastructure most people never think about. Mount Rainier's title as America's most dangerous volcano has nothing to do with how often it erupts. It comes from the sheer number of people sitting in the path of a hazard that doesn't need an eruption to happen at all, which means the danger sticks around whether or not the volcano ever becomes explosively active again in our lifetimes. And the region's response to that danger, an expanding warning system paired with large-scale evacuation drills, represents one of the most serious volcano hazard efforts found anywhere in the world, because officials understand exactly what's at stake for the communities living quietly in Rainier's shadow every single day. Stories like this one, where the real danger is quiet, slow-moving, and easy to miss until the data finally forces us to pay attention, are worth staying informed about. Understanding a risk like this is one of the most valuable things you can carry with you, or pass along to someone who might need it someday. Stay curious, stay informed, and keep watching closely to see what the ground beneath our feet is trying to tell us next.